Applying the chain rule to exponential and logarithmic functions. Welcome back. In this section, we are going to build upon our previous lessons to see how we handle more complex functions. To start, let's recall what we have already established regarding the basic derivatives of the natural exponential and natural logarithmic functions. Specifically, we learned that the derivative of e to the power of x with respect to x is simply e to the power of x. Similarly, we found that the derivative of the natural log of x with respect to x is equal to 1 over x. Now, while these basic rules are the foundation, in practical mathematics and real-world applications, such as when we are calculating the rate of radioactive decay or modeling the growth of a population, we rarely encounter functions that are as simple as e to the power of x or the natural log of x. Instead, we frequently encounter what are known as composite functions. These are functions where the exponent of the exponential or the argument inside the logarithm is not just a single variable, but is itself another function. To differentiate these more complex expressions, we cannot use the basic rules in isolation. Instead, we must apply the chain rule. Over the next few slides, I will show you exactly how to use this rule to break down these composite functions and find their derivatives. Understanding the chain rule concept. Now that we have established the basic derivatives of exponential and logarithmic functions, let's discuss the tool we need to handle more complex scenarios, the chain rule. Essentially, the chain rule is used whenever we encounter a situation where one function is nested inside another. To put this into a formal mathematical framework, if we have a composite function, y equals f of g of x, the derivative is found by taking the derivative of the outer function and multiplying it by the derivative of the inner function. In notation, this is expressed as di dx equals f prime of g of x multiplied by g prime of x. As we move forward into the specific examples involving exponential and logarithmic functions in the upcoming slides, you will notice that the process follows a very predictable pattern. I want you to think of it as peeling an onion. We differentiate the outer shell first, and then we move inside to differentiate the inner expression. Differentiating exponential composites, e.g., $. Now that we have a conceptual understanding of the chain rule from the previous slide, let's look at how we specifically apply it to exponential functions. When the exponent is not just a simple x, but is instead a function, which we will call g of x, the rule changes slightly. The derivative of e to the power of g of x is equal to the original term, e to the power of g of x, multiplied by the derivative of that inner function, g of x. To see this in action, let's look at example 1, where we need to differentiate y equals e to the power of negative x. You will often see this specific function in physics when calculating the intensity of light as it passes through a medium. We will solve this using the four-step process. Step 1 is to identify the inner and outer functions. Here, the outer function is the exponential e to the power of u, and the inner function is u equals negative x. Step 2 is to differentiate the outer function. As we learned in the first slide, the derivative of e to the power of u is simply e to the power of u. When we substitute our inner function back in, we get e to the power of negative x. Step 3 is to differentiate the inner function. The derivative of negative x with respect to x is simply negative 1. Finally, in step 4, we multiply these two results together. E to the power of negative x multiplied by negative 1 gives us our final derivative, negative e to the power of negative x. This pattern of differentiating the shell and then the inside is exactly what we will apply in the next few examples, including more complex trigonometric exponents. Differentiating exponential composites, example 2. Now that we have seen how to handle a simple linear exponent in the previous example, let us move on to a slightly more complex case in example 2, where we are tasked with differentiating y equals e to the power of cosine x. Following the systematic approach we established in the previous slides, our first step is to identify the inner and outer functions. In this expression, the outer function is the exponential function, e to the power of u, while the inner function, the part nested within the exponent, is u equals cosine x. Next, we differentiate the outer function. As we learned at the beginning of this lesson, the derivative of e to the power of u is simply e to the power of u. By substituting our specific inner function back into this result, we obtain e to the power of cosine x. Now, we move inside to differentiate the inner function. The derivative of cosine x with respect to x is negative sine x. Finally, we apply the chain rule by multiplying the derivative of the outer function by the derivative of the inner function. Therefore, the derivative of y with respect to x equals e to the power of cosine x multiplied by negative sine x for the sake of mathematical neatness. We typically rewrite this final result as negative sine x times e to the power of cosine x. Once you are comfortable with these exponential composites, we will proceed to the next slide to see how this same outer-inner logic applies to logarithmic functions. Differentiating logarithmic composites, \log gx $. Now that we have mastered the chain rule for exponential functions, let us shift our focus to logarithmic composites. When the argument of the logarithm is not just a simple variable, but a function, which we will call g of x, the rule for differentiation changes slightly. The derivative with respect to x of the natural log of g of x is equal to 1 over g of x, multiplied by the derivative of g of x with respect to x. To make this easier to remember, we can simplify this expression. The result is simply g prime of x divided by g of x. In other words, it is the derivative of the inner function divided by the original inner function. Let us apply this logic to example 3, where we need to differentiate y equals sine of the natural log of x. Pay close attention here, as the structure is slightly different from our previous examples. In this specific case, the logarithmic function is actually the inner function, and the sine function serves as the outer shell. We will follow our established four-step process. Step 1. Identify the inner and outer functions. Here, the outer function is sine of u, and the inner function, u, is the natural log of x. Step 2. Differentiate the outer function. The derivative of sine of u is cosine of u. When we substitute our inner function back in, we get cosine of the natural log of x. Step 3. Differentiate the inner function. As we learned in the introductory slides, the derivative of the natural log of x is simply 1 over x. Step 4. Multiply these two results together. The derivative of y with respect to x equals cosine of the natural log of x, multiplied by 1 over x. This can be written more cleanly as cosine of the natural log of x, all divided by x. As we move forward to the next slide, we will see how to handle even more complex scenarios where these functions are nested within inverse trigonometric functions. Complex composites, inverse trigonometric and exponential functions. Now that we have seen how to handle logarithms and exponentials as both inner and outer functions, let's look at a more complex scenario. Sometimes, you will encounter a function where an exponential is nested inside an inverse trigonometric function. Let us walk through example 4 together, where we are tasked with differentiating y equals inverse cosine of e to the power of x. Following the same systematic approach we used in the previous examples, our first step is to identify the inner and outer functions. In this case, the outer function is inverse cosine of u, and the inner function, u, is e to the power of x. Next, we differentiate the outer function. The derivative of inverse cosine of u is negative 1 divided by the square root of 1 minus u squared. When we substitute our inner function back into this expression, we get negative 1 divided by the square root of 1 minus the quantity e to the power of x squared. Now we move to the inner function. As we established at the beginning of this lesson, the derivative of e to the power of x is simply e to the power of x. Finally, we apply the chain rule by multiplying these two results together. This gives us -1 divided by the square root of 1 minus the quantity e to the power of x squared, multiplied by e to the power of x. When we simplify this expression, we arrive at our final result. -e to the power of x divided by the square root of 1 minus e to the power of 2x. This example demonstrates that no matter how complex the nesting becomes, the outer-inner process remains the same. In the next slide, we will summarize these key takeaways to provide you with a clear mental checklist for solving these types of problems. Key takeaways. Now that we have worked through several practical examples, including the more complex inverse trigonometric functions, let us summarize the key takeaways to ensure you have a solid grasp of the process. First, let's revisit the outer-inner rule. This is the core logic of the chain rule. Whenever you encounter a composite function, always differentiate the outermost function first, keeping the inner expression completely unchanged. Once you have done that, you simply multiply that result by the derivative of the inner part. When we apply this specifically to exponential functions, you will notice a predictable pattern. The derivative of e raised to the power of f of x will always contain the original term, e raised to the power of f of x, multiplied by the derivative of f of x. This is the same pattern we observed in our earlier examples with the negative x and cosine x exponents. Similarly, for logarithmic functions, there is a very useful shortcut. The derivative of the natural log of f of x always results in a fraction, where the numerator is the derivative of f of x and the denominator is the original function f of x. Finally, it is crucial to remember that the order of functions matters. You must be very careful to identify which function is nested inside the other before you begin. For example, in the function sign of the natural log of x, the logarithm is the inner function. However, if the function were the natural log of sine of x, the sine function would be the inner one. Misidentifying the inner function will lead to an incorrect result. Keep these patterns in mind, as they will help you avoid the common pitfalls we are about to discuss in the final slide. Common mistakes to avoid. Now that we have covered the rules and worked through several examples, let us conclude by discussing some common mistakes to avoid. Being aware of these pitfalls will help you ensure accuracy in your calculations. First, a very frequent error is forgetting the inner derivative. For instance, when differentiating e to the power of 2x, some students mistakenly leave the answer as simply e to the power of 2x. However, as we discussed in our earlier examples on the chain rule, you must multiply the outer derivative by the derivative of the exponent. Since the derivative of 2x is 2, the correct final result must be 2e to the power of 2x. Second, let us address incorrect logarithmic differentiation. It is a common mistake to think that the derivative of the natural log of a function is equal to 1 divided by the derivative of that function. Please remember the formula we established in slide 5. The derivative is 1 divided by the function itself, multiplied by the derivative of that inner function. In simpler terms, it is the derivative of the inside divided by the inside. Third, please be mindful of sign errors. When you are working with functions such as e to the power of negative x or e to the power of cosine x, the derivative of the inner function introduces a negative sign. Specifically, -1 or negative sine x, it is crucial that this negative sign is carried through and clearly reflected in your final answer, rather than being lost during the simplification process. Finally, be careful not to confuse the natural logarithm with log base 10. For the purposes of this course and the examples we have solved, we are using the natural logarithm, which is log base e. If you were to encounter a logarithm with a different base, you would need to include an additional constant factor in your derivative. Always verify the base before you begin your differentiation.